All right, so this presentation will talk about solubility equilibrium calculations. We're going to add in what we would have happen if we're using Le Chatelier's principle. Like we can add something or take away something, that kind of thing. So our lesson objectives will determine concentration of ions, solubility, equilibrium constants, and solubility for given initial conditions. We will define the common ion effect, and we will perform calculations involving a common ion. We know how to determine if something precipitates given the solubility values, but what about when we're given a KSP instead? In this case, we compare Q and K and decide which way the equilibrium is shifting based on our initial conditions. So without further ado, does lead 2 chloride precipitate if you add 20 milliliters of 0.5 molar lead nitrate with 30 milliliters of 0.1 molar sodium chloride with a KSP of 1.7 times 10 to the negative. So our reaction is making lead chloride, and we need to determine if any precipitate will form at this concentration given the KSP. The KSP is a constant calculated using molarities, so we need to find the molarity of our materials and then determine the limiting reactant. Let's try another one. If you have 100 milliliters of 3.1 times 10 to the negative third molar lead fluoride, and its KSP is 7.0 times 10 to the negative eighth, will any precipitate form, and if so, how much? So we're given molarity, we need to determine if a precipitate forms. So again, we need to calculate the concentration of our ions. Here we're given the concentration in moles for the molecule. So we can use an ice table and our stoichiometry. If you prefer, you can just use stoichiometry to determine the initial lead and fluoride concentrations. So we've got our equilibrium equation for dissociation, and we go ahead and plug these in. So we're going to get 1 lead for every 1 lead fluoride. We're going to get 2 fluorines for every 1 lead fluoride. There we go. So we can now put that into the Q equation. So that'll be Q is equal to 3.1 times 10 to the negative third molar times 6.2 times 10 to the negative third molar squared, which gives you 1.19 times 10 to the negative seventh for our Q, which is greater than 7.0 times 10 to the negative eighth. So it'll go towards solid. We will form precipitate. But the question asks, how much? In order to determine how much, we are in ice table territory, decidedly. Like, we can't do it with stoichiometry as an alternative feature. So here we go. So we start with our equation again. And instead of going with how much is currently dissolved, we want to know at equilibrium what's happening. So at equilibrium, we would start with 0 solid, and then we would form ions. So we have plus x plus 2x. We're basically coming at it from the opposite way. Then we take these x's, we plug them into the KSP equation, and we're given KSP, right? So now we do algebra, and we solve for x. And that x is actually going to be the solubility, because we have a 1-to-1 ratio between our lead 2+ and our molecule. So that means that we have 1-to-1 for solubility. All right, so now we have solubility. And we remember from doing stuff with solubility that if we have a concentration that's high and we have the solubility, we can figure out how much of it should precipitate once we go from supersaturated solution to saturated. So we're just going to take the difference between 3.1 times 10 to the negative third and 2.6 times 10 to the negative third. And we get 0.5 times 10 to the negative third, or if you prefer, 5 times 10 to the negative fourth. All right, so now we have the amount of stuff that has precipitated. But most people don't like to look at that type of thing in molarity, so we're going to convert it. We're going to convert it to grams. So we take our molarity times our volume in order to get to moles, and then we use our molar mass to get to grams. And we get 10 grams. And you may be wondering, why did I say 10 and not 12 point whatever? And the answer to that question is sig figs. We only have one sig fig when we take the difference of those concentrations. So we round to the tenth place. We have 10 grams of lead fluoride will precipitate. Again, rounded, it's an estimate. It's all good. At this point, hopefully after having done 2 problems, we see a pattern. If we have an ion in excess, it will push the equilibrium towards the solid form. It's not really a surprise. It's doing what Le Chatelier's principle says it should. So there's a name for this. The common ion effect. So when you add 2 solutions together and they share a matching component ion, it is called a common ion, as in you have them in common. When the common ion is added, this is the same as changing the concentration of a product, which shifts to equilibrium towards reactants. Okay, so if we're shifting towards reactants, it depends on what type of equation we have going on. That shift in equilibrium is called the common ion effect. Now, we've already seen examples of this. For acid-base chemistry, we used the common ion effect in order to calculate what's going on with buffers, their pH, their concentration, etc. We used the common ion effect to explain the pH at the equivalence point of our reaction. For an acid-base titration, we used it to explain what's going on at the midpoint. Like, common ion effect actually has come up quite frequently already. For this chapter, it will tell us the precipitate forms from the solubility equilibrium, and it will tell us how much. All right, so when we build up our understanding, we're first going to just start with the simple task of identifying the common ion. What are the common ions in the following pairs? So in the case of silver chloride and sodium chloride, both of them have chlorine. So they have a common ion of chloride. For lead-4 nitrate and lead-4 chloride, the common species is lead. Lead-4 plus is the common ion. Pretty much you can just look at it and go, what's the same between these 2 things? And that'll tell you what your common ion is. It is not rocket science. So going forward, let's try to do some math involved with this stuff that's a little bit different from what we've done previously. Okay, we're going to do a calculation with the common ion effect, which I will abbreviate as CIE, not to be confused with the other CIE that you deal with all the time. If you mix 20.0 milliliters of 0.5 molar NaCl with 20.0 milliliters of 1.00 times 10 to the negative third molar lead chloride, will precipitate form and how much? Our KSP is 1.7 times 10 to the negative fifth. We're mixing 2 things, so we're going to have a new volume and new molarities. Okay, so we go ahead and we deal with that, and it's the same basic business as what we did before, so I'm not going to be explicit about it because I know you can do it. It's not that bad. Now, when we look at this, we have 2 times 10 to the negative third molar chlorine from lead chloride, and we have 0.250 molar chlorine from sodium chloride. So we're going to add those 2 together to get 0.252 molar chlorine at the start. And if we plug that in for our KSP, we have 1 times 10 to the negative third times 0.252 squared. We get 6.4 times 10 to the negative fifth, which is greater than 1.7 times 10 to the negative fifth, and it will therefore shift towards precipitate. So we need to figure how much precipitate will form. Enter our equilibrium equation and our ice table. We know that we're shifting toward our reactant. So we have our initial concentrations. We add to the lead chloride, we subtract from the lead 2 plus and the chlorine minus, and we have an equation. We plug that into our KSP, and we look at this and realize that 1.7 times 10 to the negative fifth may actually affect 1.00 times 10 to the negative third, but it will do squadoosh to 0.252. So we're going to approximate 0.252 minus x as just being 0.252. And our x is, after we do that, equal to 7.5 times 10 to the negative fourth. Okay, so from there, we know how much precipitate has formed in molarity, but we need it in grams because that's usually how we talk about the thing. So we take the molarity, we multiply it by the volume, and we multiply it by the molecular weight, and we get 8.3 times 10 to the negative third grams of lead chloride precipitate. Which isn't that much, but it happened. It shifted toward precipitate. Okay, what else? All right, so let's calculate molar solubility from molarity and KSP. And this particular problem is the see if you understand it problem from this portion of the worked problems in the book. So we're going to calculate the molar solubility of aluminum hydroxide in a 0.15 molar aluminum nitrate solution. So the 0.15 molar aluminum nitrate gives you a source of aluminum ions, and we're going to assume that we have some aluminum hydroxide solid just kind of like hanging out in that mixture. The KSP of aluminum hydroxide is 2 times 10 to the negative 32nd. So we start out with our equilibrium equation. We've got aluminum hydroxide in equilibrium with Al3 plus and 3 OH minus. We set up our ice table, and we know that we're going to have 3 times as much hydroxide as we have aluminum from the same amount of aluminum hydroxide. So we don't bother with the initial concentration of the solid because it doesn't matter in the equilibrium expression anyway. We just leave that blank. We have 0.15 molar Al3 plus, and we have no hydroxide to start with. So we add plus x from the aluminum 3 plus, we add 3x to the OH minus, and we get our equilibrium at 0.15 molar plus x and 3x. We plug that into our KSP, and we have 2 times 10 to the negative 32nd is equal to 0.15 plus x times 3x cubed. Now, 2 times 10 to the negative 32nd is super tiny. So when we say 0.15 plus x is going to be inconsequential to that, and we are just going to approximate that to be equal to 0.15. So that simplifies our equation to 0.15 times 27x cubed is equal to 2 times 10 to the negative 32nd. And when you divide both sides by 27, divide by 0.15, and then take the cube root of what's left, you get x is equal to 2 times 10 to the negative 11th molar aluminum hydroxide. That is how much actually dissolves. So the molar solubility is 2 times 10 to the negative 11th in this particular solution. To be clear, it would not be exactly that number if you didn't have a common ion. All right, so that pretty much takes us through all of the basic ideas from this chapter, or not this chapter, but this section of this chapter. And hopefully you guys will be able to do some problems, get started on your homework, and try to conquer the solubility equations. Solubility is the maximum amount of solute you can dissolve in water, i.e. a saturated solution, often given in grams of solute per 100 grams of water. So there's going to be some unit conversions involved with these problems. Solubility product, or KSP, is the equilibrium constant describing a dissociation equation. And when you add 2 solutions together and they share a matching component, it's called a common ion. When that ion causes precipitate to form, that is the common ion effect. Really, it's the shift in equilibrium, a la Le Chatelier's principle, because of the common ion that we're talking about.